Hi there, so I'd like to fill in this list of basic functions handout with you. Again, you're welcome to print this handout or maybe make a similar one by hand, whatever works best for you, but it is available to you. And so these are functions that you should be more or less familiar with as we move throughout the rest of the semester. We'll be referencing them, and you should kind of have an idea of what their graphs look like. So the first one up is just the identity function. The idea is that whatever we plug in is the same thing that comes out. So that's why if there's an x here, there's also an x there. So the domain of a function like this, and actually let me maybe graph this as we go. This graph is just a linear graph, and we can make note of that. This is linear. Where our slope is just 1 over 1 if you'd like, and our value of b is 0, 0. It goes through the origin. So we've got a point here, rise 1, run 1, rise 1, run 1. You get an identity that just cuts straight down the middle. Okay, so the domain of a function like this, and again, we're going to pretend my lines are a little straighter. I'm a little wobbly on this device, but our domain is going to be the set of all real numbers, so negative, infinity to infinity. You could also say R, where there's 2 lines on the back. And the range is actually also negative infinity to infinity because all numbers get used, right? The domain, if you remember, is representative of our x values. So it's as we move from left to right, which x values get used. And the range, remember, is representing the y values as we move from bottom to top, what values get used, okay? And in this case, all of them. This function is actually increasing for its entire domain. You can see that the function rises, again, as we move from left to right with x values. So this is increasing on negative infinity, infinity, and it's not decreasing anywhere. So you could maybe just say none. That would be sufficient. There's also not really going to be a maximum or minimum value, either local or absolute. As you can see by looking at our picture, there's no tallest point, there is no lowest point. So in this case, we would say none as well. Okay, so that is our first function. We're going to scroll down to the second one. So the squaring function is something you might be somewhat familiar with. You could think of this as a quadratic function. So you can think of this as a quadratic function, and the graph specifically is going to be a parabola. It's centered at the origin. There's no shifting or movement or anything else attached to it. So your graph will look something like this. And these are just sketches. We're not going to be maybe quite as precise where we're measuring out points, but you should be as close and as accurate as possible. The domain of this function, again, the x values, is the set of all real numbers, so negative infinity to infinity. The range, however, starts at y is equal to 0, and that number 0 is included, so we use a bracket, and it increases indefinitely, or forever, it would be a better way to say that, so it goes till infinity. So again, a bracket is there because that 0 value gets used. This function is only increasing from 0 onwards, so this is going to be from 0 to infinity, and again, that's a comma, and it's decreasing on that first portion of the graph from negative infinity to 0. Okay? This function also does not have a maximum. You can tell again by looking at this picture, there is no tallest point. So there's none there, but there is a minimum value, right? Do you see that the lowest point on this graph, and we can even say it's an absolute, absolute minimum, is going to be at that point 0, 0. Let me write it so it looks like a comma. There we go. And then by extension, it's also a relative minimum that, if it is absolute, it's also relative. Okay? So if we keep going, you have your cubing function, and some of these, this is one of them, have some just cute little nicknames that I've seen over different courses that I've taught, different textbooks. I love this one. We call this John Travolta dancing. Dancing. The reason for that, hopefully that's not too dated of a reference, but the reason is because the graph looks like this, which is a little harder to do not in person, but it looks a little bit like disco, right? You have somebody's hand maybe up here on this side, and their foot sticks out on this side. I can throw an image of this into this if you'd like, but that's kind of the idea behind it. I think it's kind of a fun way to remember this graph, so take it or leave it. But this is what the graph of our cubing function looks like. Again, you're always welcome to plot points if you're not 100% sure what this looks like originally, but we want to get to a point where we memorize this. The domain is still the set of all real numbers, and we actually return to the same for our range. If you notice, right, all y values are used and all x values are used. This function is also increasing for its entire domain. Okay, and it's not decreasing at all. Okay, and in addition, because there's no change from increase to decrease, there's no maximum and there's no minimum. Okay. Let's keep going. So the square root function is kind of an unusual one. It starts here at the origin, and then it kind of branches out like this. One way that you can remember this is like half of a parabola. Unofficially, you can kind of see this other half here, but if this is there, do you notice we failed a vertical line test and we're not a function, right? So we actually don't keep that bottom half. We only keep the top half of it. And that's where we're using that idea of a principal square root. That means that when we take the square root of a number, say like 9, our answer is only 3, not plus or minus 3, okay? That's the idea behind a principal square root. Okay, so the domain of this function is actually starting at x is equal to 0, and 0 is included, so a bracket, and then it goes on forever till infinity. The range is the same. We're starting y values at 0 and then moving up to infinity. Okay, this one doesn't really have as like cute of a name, but I've seen this called right turn. So if that works, if that helps you remember it, go for it. This function is only increasing, so it increases again from 0 to infinity. Remember, with increasing and decreasing, we always use open parentheses, no closed brackets. It's not decreasing. Okay. There is no maximum point here because it just continues on towards infinity, but there is a minimum point, and that's at the origin. And I labeled this as absolute last time. We can do the same thing. There we go. And then again, by extension, this is also relative. Okay, let's keep going. The cube root function is kind of like the cubing function, but a little flipped on its side. We'll see that inverse relationship in the next section. So this kind of goes like that. It's like John Travolta had a little too much to drink at his party and he fell over. So this is your cube root function. The kind of cute name that I saw for this was Michael Phelps. Because it kind of looks like somebody swimming, right, where they're using their arm to stretch out and their foot's kicking on the other side. If you could switch it out for like some other swimmer. I think the only one I know of is Ryan Lochte, but again, name it whatever you want, but it looks kind of like a swimmer. The domain and the range are both all real numbers. And this function is only increasing. Awkward. It's not going to be decreasing. As well, there's no maximum and there's no minimum. And I think you'll find that happens with a handful of functions. We're not guaranteed that all of them have that, but okay. We also have the rational function. Now we're going to kind of start this off and then we'll get more details with this later on when we do chapter 4, which is much later in the semester. Kind of like this and this. This is a pretty unusual graph. It relies on asymptotes, which again, we just won't formally talk about just yet. You might have talked about them in an 095 class, but somebody once recommended calling this a baseball. They were obviously a huge baseball fan, but it kind of reminded them of the stitching on a baseball and the way those two sides are drawn. You could draw this side a little closer. There we go. Okay, so the domain of this function is kind of weird, and it's because we have this denominator value. That x in the denominator cannot be 0, so our domain goes from negative infinity to 0, union 0 to infinity. We can't actually plug 0 into this function. You see something similar as we move from bottom to top for our y values. The output, the answer, will also never be 0. So negative infinity to 0 as well, negative 0 to positive infinity. So they have the same answer, but kind of for different reasons. This function is actually never increasing. If you look on both of these as we draw them from left to right, on both sides, we actually are moving downward. So it's decreasing from negative infinity to 0, union 0 to infinity. Okay. There's not really a maximum or a minimum value attached to this either. We'll see some down the line that are maybe curved a little differently. Maybe they're a little bit more like this. In their drawing, ours isn't really like that, so there's not necessarily a maximum or minimum. It also has to do with the fact that we have asymptotes, which we can circle back around to later. This is a similar idea. It's the rational function squared, and actually what that looks like is, there you go, like that. A little smoother. Okay, so the domain of this function is going to be actually the same, negative infinity to 0, union 0 to infinity, but our range is going to be different from the previous question because there's no graph down in this bottom portion. So we only have from 0 to infinity. Again, bottom to top, that's how we measure range. So this function is increasing for part of its domain. It's increasing from negative infinity to 0, and it's decreasing from 0 to infinity. There also is no maximum and no minimum. Again, that has to do with asymptotes. We're not actually equal to those values where x is equal to 0, y is equal to 0. They're not actual outputs. Just as before, our function is undefined when x is equal to 0, and we'll never get 0 back as an actual answer. Okay, we move up here to absolute value. We're actually going to stop at this one. We'll circle back around to add the exponential growth after the next section, next 2 sections from now. But for absolute value, I saw this once as absolute Somebody said absolute victory because of that letter V that's sitting there. This graph looks like a V. What actually it is it's actually a straight line, very much like that identity function. But because we're making all of our output values positive, everything that's down here, down below, gets flipped up here instead. In other words, they're made positive. Now, you don't need all that extra stuff on this graph, but that's just kind of where it comes from. It's like we took a straight line and broke it and bent that bottom part up. So its domain is still all real numbers. We can plug in whatever we want. The range, though, only goes from 0 included to infinity. It's increasing on the second half of that picture. So it's increasing from 0 to infinity, and it's decreasing on the first part. So that's negative infinity to 0. There is no maximum point. However, there is a minimum down here. Okay, so that's a decent list of everything we've got. There's only 2 we have not covered, and we'll get to those in the next section, so we'll cover them pretty soon. Okay?